Hi everyone, welcome to the post-contest discussion of the Codeforces Round 981, and I am Abhinav and this is TLE Eliminators. Let's get started with the first problem. Okay, so in the first problem, we are given that Sakurako and Kosuke decided to play some games with a dot on a coordinate line. The dot is currently located at position x equal to 0. They will be taking turns and Sakurako will be the first one to start. On the ith move, the current player will move the dot in some direction 2i minus 1 units. Sakurako will always be moving the dot in the negative direction, and the other player would be moving in the positive direction. So what is happening? You start with they start with x equal to 0. In the first turn, Sakurako would make it minus 1, x equal to minus 1. Then Kasurako will change the position by 3, so he moves it in the positive direction. So minus 1 plus 3 is 2. Then this guy moves in the negative direction. So he'll do a minus 5. So 2 minus 5 becomes minus 3 and so on. It would go. Now they will keep on playing while the absolute value of the coordinate of the dot does not exceed n. More formally, the game continues up till this. Okay, so till this x, this is minus 1, this is 2, this is minus 3. So until the absolute value doesn't exceed n, the game would continue. After that, the game would end. Your task is to determine who will be the one who makes the last turn. Okay, so you just need to determine who would be making the last turn. So in input, you are given t test cases. Every test case has just an integer n. Okay, so if you just analyze what you need to do, let's say n is 6. Okay, so what you need to do is, let's say as an input, you are given n equal to 6. What it means, so like I'm denoting by player 1 and player 2. Okay, the what player 1 does, you are on a number line at x equal to 0. Player 1 would they would move their turns in 2i minus 1. Okay, so in the first turn they would change the position by if you put I equal to 1, this thing would give us 2 minus 1 1. Okay, and at I equal to 2, this would give us 3. At I equal to 3, this would give us 5. So basically we are moving to every odd integer. First turn it would be 1, then 3, then 5. Okay, so first turn would be taken by player 1. He would move it in the positive direction. Okay, sorry, the first turn was in the negative direction. Okay, player 1 moves in the negative direction, so minus 1. So it was here at x equal to 0. It would be moved to x equal to minus 1 in the first turn. Then the second turn is taken by player 2, and he would take it in the positive direction, so a plus 3, and it would take it to 2. Then third turn is by the first player again. He makes it in the negative direction. So it would be minus 5. So minus 1 here, plus 3 here, and minus 5 here. So minus 5 would make take it to minus 3. Okay, so after that, next would be 7. So a plus 7 from here. So minus 3 plus 7 would take it to plus 4. Okay, so you can notice at the first turn, when the first player moves, we went from 0 to minus 1. After that, we went to 2. After that, we went to minus 3. After that, we went to 4. Then we would move to minus 5, 6. I hope you understood the pattern in which we are moving. Okay, until what we have to move? Till the absolute value reaches n. Okay, here n was 6. So we would move till the absolute value reaches 6. After that, in the next turn, we would have moved to minus 7. But we would not move to minus 7 because at this is n, so at 6 we would end. Okay, now we just need to find which player makes the last move. Okay, so initially we were at 0. Now player 1 makes the first move, makes it negative. Player 2 makes the second move, makes it positive. Player 3 makes it negative. Sorry, player 1 makes it negative again. Player 2 this. So you can see that all the negative values are by player 1. Okay, so negative values are by player 1 and positive values are by player 2. Okay, and if you look at the values, all the negative values, we are moving minus 1, 2, minus 3, 4, minus 5. So what all values are negative? 1, 3, 5, these are odd numbers. So one more way of saying is negative, or you can say the odd values are by player 1, even values are by player 2. So just by looking at this pattern only, you can understand that if the absolute value of my sum is odd, then it's by player 1. If it is even, then it's by player 2. Now, when would the game end? We are moving from 0, 1, 2, 3, 4, 5 up till n. So the last move is n. So if n is odd, we would say player 1 is making it. If n is even, we would say player 2 is making it. So my final code would be just, we would just check that if n is odd, n modulo 2 is 1, then we would say it is odd. Then the first player, the name of the first player is Sakaraku. Okay, Sakaraku will change the position to -1. It can prevent it again or determined will be the player to me. So if it is odd, Kasuke is okay. I think for okay, the last turn is by if it is odd, keep on playing absolute. Okay, so if n is 6, it means when we go to -7, then the game is ending. Okay, so if this is even, it means n plus 1 is the basically the value till which we are going, and then the game is ending. So we can, okay, finally it would be just that only. If n is odd, it means n plus 1 would be even. That means player 2 is winning. So if n is odd, the player 2 was Kasuke. So we would say that uh, Kosuke is winning here. Okay, or else we can say that the other player is winning. Okay, that's what we had to like output in our write in our code. Okay, you can look at the code also now. If n is odd, then Kasuke, else Sakuraku. This was it. Okay, from the test cases also you can see, from observing the pattern also you can see. I hope this first problem is clear to everyone. If anybody has any doubt, you can say now, or we'll move to the next problem. Okay. I hope the first problem is clear to everyone. It was just simple, just by looking at the pattern only, you can understand it. So let's move to the problem B. Okay, in problem B, during her
सर
journey,
लास्ट लास्ट
yeah.
वाले पार्ट में सर जो आप चेंज किए हैं वो नहीं आया समझ में सर।
Okay, like इसमें जो बेसिकली
हाँ
एन ऑड है, ये नहीं समझ आया। यहाँ पे लाइक वी वर स्टार्टिंग विथ 0। ओके, इनिशियल पॉइंट वाज x इक्वल टू 0। तो लाइक गेम कब एंड हो रहा है, लाइक यू कैन सी द पैटर्न ओनली कि 0 के बाद -1, तो -1, देन वी डू अ +3, तो 2 पे गया, देन वी डू अ -5, तो ये 3 पे गया,
सर
-3
ऑड
पे।
आ रहा है फिर तो प्लेयर वन जीतेगा ना सर।
हाँ, तो ये लाइक देख लो, द गेम कंटिन्यूज वाइल दिस, तो until x is less than or equal to n, गेम इज कंटिन्यूइंग। जब n से बड़ा हो जाए, देन द गेम इज एंडिंग। ठीक है, तो अगर n इक्वल टू 6 है, तो -7 पे गेम एंड होगा। ओके, तो
ओके।
अगर n ऑड है, लाइक इस केस में n इवन था, तो -7 पे गेम एंड हुआ, और -7 प्लेयर 1 का था, ऑड वाला। तो इवन पे प्लेयर 1। ओके, लाइक समझ गए ना? जस्ट तुम सैंपल पे देख सकते हो, ऑड पे कासुके है, इवन पे साकुराकू है। तो लाइक दो ही केस था, सैंपल से ही देख सकते हो। ठीक है, आई होप इट्स क्लियर। ओके, लेट्स मूव टू प्रॉब्लम बी। During her journey with Kasuke, Sakurako and Kasuke found a valley that can be represented as a matrix of size n cross n, where at the intersection of the ith row and the jth column is a mountain of height aij. If aij is less than 0, then there is a lake there. Kasuke is very afraid of water, so Sakurako needs to help him. With her magic, she can select a square area of mountains and increase the height of each mountain on the main diagonal of that area by exactly 1. Okay, more formally, she can choose a submatrix with the upper. Okay, that's only is given in mathematical form, what is written here. Determine the minimum number of times Sakuraku needs to use her magic so that there are no lakes. Okay, like I'll explain you with the test case. Okay. So in this problem, what it said, you are given an n. Okay, so here n is 3 and then a matrix of n cross n. So if n was 3, we are given a matrix of 3 cross 3. Now, what does this matrix represent? It represents, so like, let's draw this matrix. Okay, it's 1, 2, 3, minus 2, 1, minus 1, 0, 0, minus 1. Okay, so like in this matrix, what you can do is the positive numbers represents mountains, negative numbers represents lakes. Okay, so its depth is negative, it just represents lakes. So this is just for the story. What you need to do in the problem, according to the problem statement, is you can just choose any submatrix of square size, any square submatrix. Okay, so you can take a 1 cross 1 submatrix, or you can take some 2 cross 2 submatrix, or you can take this complete 3 cross 3 submatrix. Okay, let's suppose you chose this 2 cross 2 submatrix. Then what you can do is, in this, whatever the diagonals are, the diagonals of this square matrix, you, in those diagonals, you can do a +1 to every element. Okay, so what would happen if you choose this submatrix? In these diagonals, that is in these two values, you can do a +1. Okay, so 1 would become 2, minus 1 would become 0. Okay, so this is one operation that you can do. Okay, so this is the operation that you can do. Now you need to find out the minimum number of times Sakurako must use her magic so that there are no leaks. Okay, basically there are no leaks. It means all the values become uh, greater than equal to 0. Okay, there are no negative values. That's what you need to do. Okay, so you need to apply the operations. So in one operation, you can select a submatrix, and in all the diagonals, you can do a +1. That's one operation. You need to find in minimum number of operations. You can make all the values in this matrix as greater than equal to 0. There are no negative values remaining in this matrix. That's what you have to make sure in minimum number of operations. So you need to find the minimum number of operations. I hope the problem statement is clear. So like for this test case, what was the answer? It was like you can choose this matrix and add a +1. Then what would happen? It would become 2, it would become 0. Then maybe you can choose this single submatrix. There is one element, and that would be the diagonal only. So you do a +1, it would become 0. Then you can choose this submatrix. Okay, and you can do a +1 here. It would become -1. You can choose it again and do a +1. It would become 0. So one time we chose this, then we chose this, then two times we chose this. So a total of 4 operations. After that, the matrix has all element positive or 0. Okay, so in 4 operations, we were able to do it. So for the third test case, you can see 4 was the answer. You can do it in other ways also, but the minimum number of operations required here would be 4. You cannot do it in less than 4 operations. So my answer was 4. Okay, I hope the problem statement is clear. Now, how can we solve this? Okay, so like if you look at the operations, okay, what is the type of operation that we are doing? Okay, we can just select any square submatrix and add a +1 to the diagonals. Okay, like in fact, if you see, it's just any diagonal. You can just select any diagonal. Okay, if you just select any diagonal, that represents a square submatrix. If you select a point if you select the starting and ending points of any diagonal, then they would form a square submatrix, and that would be its diagonal. So basically, instead of considering this square submatrix, you can directly say just select any diagonal of the matrix and do a +1 to all the elements. That's what effectively this operation is. So how many diagonals, what all diagonals does this matrix have? It has a every element in itself is a diagonal of its own submatrix. Okay. So this is one diagonal. Then we can have this in itself is a diagonal, this in itself in a diagonal. But this is also a diagonal. So if you look at this, if I'm like selecting this and Another way is selecting this in one operation and this in another operation. So what would always be better? It would be to select this whole. It would never be beneficial to do it one time, because if you are in if something is already positive and you are increasing it, there is no problem in that. But if there was a -2 and a -1, then in two operations you can just make it 0, and this would also become a +1. But if you are doing differently, a -2 and -1, two operations here, one operations here, you would be using three operations. So that is never beneficial. So you would always take the full length diagonal. So what I'm saying is, you would check this diagonal, then this full length diagonal, this full length diagonal, this full length diagonal, this full length diagonal. Okay. So whatever matrix you have, let's say you have some bigger matrix, whatever n cross n matrix you have, 1, 2, 3, 4, 5, 6. Okay, let's say you have a 6 cross 6 matrix. What all diagonals would exist here? We would check this diagonal, then this, then this, then this, 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 and this. Like if you just check all of the diagonals, if you just check in all of the diagonals, then for any particular diagonal, what's the minimum value you would need to add so that all the elements become greater than equal to 0? You would have to add that much at least. Okay. So you would say for this diagonal, in this, there is only one element. So if it is greater than equal to 0 already, we would say we do a +0 operation, no operation required here. Like in this diagonal, among these, just take the minimum element. The minimum element would be the element that would require the most number of operations in order to become positive. So take the minimum element among these elements. If that is less than 0, then how much negative that is, that many operations would be required. Same for this, same for this, for this, for this. So for every diagonal that you get, all these diagonal that I have drawn, calculate the minimum among these. And if that minimum is greater than equal to 0, just ignore that. If that is less than 0, then add the absolute value of that to your answer. You would require that much operations to at least that much operations in order to make all of them positive. I hope you got the logic, what I'm trying to say. So for this case, what you would do, you would check this diagonal. Here, the minimum element is 3, which is greater than equal to 0. So you do a +0, no operation required here. You check this diagonal. The minimum element is -1. So you would do a one operation to make it 0. Here the minimum element was -1. So again, you do a +1 operation. Here the minimum element was -2. So you do a 2 operations. Here minimum element is 0. So you don't do any operations. So the sum of these values, which is 2 plus 1 plus 4, is 4. So 4 is my final answer. Okay, that's how I am getting it. So I hope you understood the logic of this. Basically, the main thing to understand here was the type of operation that you were given. You were told that you can select any submatrix and select a diagonal, which was same as just selecting any like any diagonal way, just select any sequence of elements in the diagonal. And it was always best to take the whole complete diagonal in order to like do the operation, because there's no problem in increasing the values above 0. Okay, you just need to make all the values positive. So in one operation, if you're increasing more values, there's no problem. So what you need to do in the code is just go to every diagonal, take the minimum. If that minimum is less than 0, add its absolute value to your answer. Okay, now let's move to the code. We would look how we are going to traverse these diagonals. Okay, so like for traversing these diagonals, what you can say is, okay, I'll let's number it. Okay, I'm taking a 0 based indexing in my code. So for n equal to 6, this would be the scenario. This would be my indexing of my matrix. Okay, so First, I would try to go through all of these diagonals. Okay, so my this is my row number, which would be represented by I. This is my column number, which would be represented by J. So this is 0, comma 0. Okay. So like I'm starting with every value. So I'll fix my I as 0, 1, 2, 3, 4, 5. Likewise, so I'll fix my row number one by one as 0, 1, 2, 3. And then from that, we would just go to the next column, and likewise if I'm going to one column to the right, I'm also reducing my I by increasing my I by 1. So I can say my this diagonal would be I plus j comma j. Okay, so for a fixed I would move my j from 0 to n, and that way I will go. Okay, so let's look at the code, you will understand better. Okay, so what I'm doing, I just took the input array of n cross n, and then I'm first traversing through these. Okay, this. So I'm running a loop for I from 0 to n minus 1. Okay, so this loop is I for 0 to less than n. Okay, so this rep is just for I equal to 0 to less than n. Then what I'm doing, okay, so with I equal to 0 fixed, okay, if I is fixed to 0, then I have to go to all these elements and compute their minimum. So I would initialize a minimum variable as 0. Okay, if something positive is there, we don't care about it. We only care about the negative numbers. That's why I initialize my minimum to 0. Otherwise, in general, we initialize the minimum to some very high infinity big value. Okay, but here we don't care about positive numbers, so we initialize it with 0. Then we move our j. Okay, so if we want to traverse to all the elements, um, the column number is 0, 1, 2, 3, 4, 5. For these, the column numbers is changing from 0 to 5. So we run a j loop from 0 to n minus I. Okay, so for I equal to 0, we are going up till 5. For I equal to 1, we are going up till 4. For I equal to 2, we are going up till 3. So we are only going up till n minus I. So j is running from 0 to n minus I, and we take the minimum. So my element would be I plus j comma j. Okay. So if I'm at some j here, okay, if I'm in this row, then what's my row number? It's actually whatever I fixed. I've started with I equal to 0. I went to 3. So it is actually I plus j is my row number. Okay. When I start with I equal to 1, I this would be 1 plus 0, 1. Okay. Then when I move j equal to 1, this would be 1 plus 1, 2. Okay. When I move to j equal to 2, this would be 1 plus 2, 3. Okay. So likewise, I am moving. So basically my diagonal element is I plus j comma j. Okay. So I take the minimum of mn and I plus j comma j. This way I took the minimum of that whole diagonal, and then I added that to my answer, minus of minimum. Okay, so minimum would be some negative number. Minus of that would give me the absolute value. That many operations are needed, or 0. So if okay, this 0 was not required because I already initialized my minimum with 0. So if it was initialized to some big value, then this max of 0 comma minus mn was required. Here you can directly write answer plus equal to minus mn. That would also be fine here. Okay, but just for extra safety, I'm not adding any negative to my answer. So that's why I take max with 0. So this was the whole thing for all of these diagonals. Now, I want to also traverse to these diagonals. So for that, I would fix my column number one by one. One by one, my column number is fixed to 1. Then my column number is fixed to 2. Column number is fixed to 3. That way. So I fix my j from 1 to n. Okay, I start with 1 up till n for all these elements. And then I'll move my row number one by one. Okay, so this is row number 0, 1, 2, 3 up till, for j equal to 1, we go up till 4. For j equal to 2, we go up till 3. So we are going up till n minus j, okay, less than n minus j. So again, we initialize the minimum variable, and for I from 0 to n minus j, we take the minimum. Same thing. Now the element would be a of I comma j plus I. Okay. So I hope you understand. This would be I comma j plus I. Okay. So now again, answer plus equal to this same thing. So this way we have traversed through all the diagonals, added the minimum of that diagonal to our answer, and we print our final answer. I hope this problem is clear to you. If there's any doubt, you can ask.
Your voice isn't audible.
Hello, am I audible now?
Yeah, now audible.
Okay, I'm really sorry for the interruption. Okay. So what I was explaining is the time complexity. So if you look at this, the input is order of like n times and again n times. So n square input, and then this loop is running n times. This loop is also running n times. So order of n square, this loop, and then this is n times inside that. This is also running at max n times. So n square here as well. So overall time complexity is n square and n square. So overall it's n square. Space complexity also, again, we have an array A which is of size n into n and no other variables as such. So space complexity is also n square. And if you look at the constraints, n was up till 500 only. So there was no problem. Sum of n over all test cases was 1000. So n square is well accepted. I hope this problem is completely clear to everyone. If there's any doubt, you can ask. Okay, so we can move to the next problem now. Okay, so the third problem is even in university, student need to relax. This is why it is known that all the students will be working in a line. The student with index I has some topic of interest which is described as AI. As a teacher, you want to minimize the disturbance of the line of students. The disturbance of the line is defined as number of neighboring people with the same topic of interest. In other words, disturbance is the number of indices j such that aj is equal to aj plus 1. In order to do this, you can choose index I and swap students at position I and n minus I plus 1. You can perform any number of swaps. Your task is to determine the minimum amount of disturbance that you can achieve by doing the operation described above any number of times. Okay, so basically you are given an array. In that you can do some operations of this type where you can just swap I with n minus I plus 1. Basically the first element can be swapped with last, second can be swapped with last second, and so on. And that's the only type of swap that you can do. And after doing those swaps, the minimum amount of disturbance that you can achieve, where disturbance is defined as if you have two consecutive values, two consecutive same values, that's a plus one disturbance. Two consecutive same values, that's a plus one disturbance. So you need to swap these numbers so that you minimize the number of disturbances. Okay, you can just do any number of swaps. That's the final answer you need to print is the minimum number of disturbance that you can achieve. So if you look at the first test case, so here you can see that this was our given array. So what's the swaps that you can do? The first can be swapped with the last. The second can be swapped with the last second. This first, third can be swapped with itself. So no benefit of that. So that's the only two types of swap. So either you swap one, two, and if you again swap them up, it would again become the same thing. Okay, so you would only do one type of swap one time only because doing it two times would just cancel out the previous effect. So if you do this swap only, then it would become two, it would become one. Okay. So if let's suppose you do this swap, your now the array becomes one, two, one, 1 and 3. Okay. Here the number of disturbances is 1. Okay. So there is no other two consecutive equal value index. If you look at these two values are different, these two values are different, these two values are same, these two values are different. Okay. So there's only one consecutive index which have same value. So here the number of disturbance would be 1. So by doing this swap, initially, if you look, there was one disturbance and two disturbance. So there were two values, two pair of values which were consecutive and equal. So here there were two disturbance, but by doing this swap, you reduce the disturbance to just one. Okay. And if you do try to do any more swaps, you cannot reduce it less than one. Okay. If you swap this one and three, it would become a three here, one here. Then again, you would have two disturbance. It would increase the number of disturbance only. Okay. So the best was doing this swap and making it one. So this is the problem statement that you need to find the minimum number of disturbance. I hope that is clear. Now, how can you do that? You can look at the constraints that n is up to 10 to the power 5. Okay. So, if you analyze it, like what you can do is you have an array. Okay, this array is of size n. Now you can swap the first element with the last, second with last second, third with last second, third, and so on. Now, every swap would have two options. Either you swap it or you don't swap it. Okay, so like you can understand this array is as you are dividing this array in two parts. Okay, the mirror image of these parts. Okay, so this and this element, they can be interchangeably placed, either one element here and one element here. Okay, so either you keep as they were, you keep here, you have a1 and you have an. So either you keep a1 here, an here, or you keep an here and a1 here. Okay, there is no other option. So in the first position, either you would have a1 and at last position an, or at first position an, last position a1. So if you don't perform this swap, this would be the position. If you perform this swap, then this would be the position. There are only two options for this pair of positions. Now same for this pair of positions. If you look at a2 and a n minus 2, Either it would be A2 and AN minus 2 or AN minus 2 and A2. These are the only two options. Okay. So we can see that for every like element, we have two options. Either don't swap or swap. Okay. And this we have to do up till every pair of elements. So there would be n by 2 pair of elements. Okay. Like till the middle element when you reach. Okay, you are moving in these type of pairs. So when you reach the middle element, after that, again, you are repeating it. So no need to repeat. So up till n by 2, you would have about n by 2 pairs. For every pair, you have two options, either swap it or don't swap it. So like, and finally, you need to compute if you perform either of the options, finally, what's the minimum number of disturbance you can achieve? And disturbance is determined by if you are at this index, just take the difference between those two, like these are same or not. Okay. At this index, these are same or not. These are same or not. That's what the disturbance is determined by. So with this, like you would have got a little feeling that we can easily do this with DP, that at every index, like every pair of index, we have two options, either do a swap or don't do a swap. And if we do a swap or don't do a swap in both the options, our value at that index is fixed. If we don't do a swap, then at this index we have A1. If we do a swap, at this index we have AN. And if we know the fixed values, then we can just calculate whether we add a +1 to the disturbance or a +0 to the disturbance. So it would be easily computable. The DP states would be easily computable from I. If you know the fixed value of I minus 1, you can just easily compute that. So I hope you would have got a feeling why we are going to use DP here. So what would be the DP state? It would be basically if you have went till the ith pair. Okay. Here we would be moving pairwise. So we'll only go up till n by 2th index. So if you are at the ith index, we are covering the first I values as well as the last I values. So in this, the first I values plus the last I values, if we consider this much array, and the for the ith value, either we would have a 0 or a 1. Okay. So we would have Boolean value 0 or 1. 0 represents that the ith value is, let's say, not swapped. 1 represents that the ith value is swapped. Okay. So if the ith value is not swapped, then up till, so like for first I elements and last I elements, what is my answer? Basically, the minimum number of disturbance is what my DP state is what my DP is storing. Okay, the minimum number of disturbance for the first I elements plus the last I elements. That's what my DP state represents. DP I0 is when the ith element is not swapped. DP I1 is when the ith element is swapped. Yeah. Sorry. So I hope you understood what my DP state is. Now, I think we can easily write the transition here. Non-DP solution, maybe greedily also you can do in some manner, would have to think. During the contest, I thought of the DP solution only. So maybe some greedy solution also would exist for that, for it. But currently I have done it with DP, so I'm explaining that only. We'll have to think about it. Okay. So now once I've explained you the state that I am taking, this was my state. Now, what would be my transition? Okay, I'll write my transition. So my DPI 0. Okay, one by one, I'll write my transition for I0 as well as for DPI 1. Okay, so in I0, what I'm telling is in my array, if I am at the ith element, okay, this is AI, and this is, let's say, A of n minus I. Okay. So for this much array plus this much array. Okay. For this much array plus this much array, what is the minimum number of disturbance? That I can write in terms of dp I minus 1. That for this much array and this much array, if we know the number of disturbance, so either it would be the same. Okay, it would be dp I minus 1 only, and here I'm not doing a swap. It means here I would have I minus 1, here I would have a n minus I only. Okay, so if I'm not doing a swap, so either I take whatever was up till here, the number of disturbance, and then okay, and till here again, here it would we would have two options. Either a zero, it means we are not swapping. So a I minus 1 here, a n minus I plus 1 here. This would be the case for not swap. And for the case of swap, here a n minus I plus 1, here a I minus 1, they would be swapped. So we'll take the minimum among both. We need to finally minimize our answer. We'll take the minimum among both cases. So for I minus 1, once we would consider that they are not swapped. If they are not swapped, then whatever was the number of disturbance still here, in that, if there's a disturbance here, we would add. If there's a disturbance here, we would add. Okay. So plus, we would check if a, here we have a of I minus 1 only. So if ai is equal to a I minus 1, then we would add a plus 1. And same way, if a of n minus I is equal to a of n minus I plus 1, then also we would add a plus 1. Okay, so this whole thing can be written as one possible way if this was not swapped, if we are using dp I minus 1 0. Or we can also use dp I minus 1 1. In that case, here I would have n minus I plus 1. Here it would be a of I minus 1. So ai would be checked with a of n minus I plus 1, and a n minus I would be checked with a of n minus I, a of I minus 1. Okay, so we'll take the minimum among these two. We'll take the minimum of either this whole thing or this. Okay, whichever is minimum, that would be my state for dpi0. Now same way we can write for dpi1. Okay, these two would be like swapped. For I1, these two things would be just swapped. Okay, so with I minus 1 0, we would have this. With I minus 1 1, we would have this. Okay, if we have swapped in that position. So
सर
same way you can write the state for this. Yeah.
एक बार आप फिर से एक्सप्लेन करोगे, थोड़ा कंफ्यूजन सा क्रिएट हो रहा है।
Okay. Okay, like तुम्हें क्या समझ नहीं आया, स्टेट या फिर ट्रांजिशन? स्टेट।
ट्रांजिशन नहीं समझ आएगी कैसे हो रही है, क्योंकि अ, हो सकता है कि अभी करंट वाला हम स्वैप करके ऑप्टिमल आंसर पे ना पहुंचे।
ओके। ओके, देखो, लाइक मेरा स्टेट क्या है कि dpi0 इज कि मैंने फर्स्ट आई एलिमेंट और लास्ट आई एलिमेंट जस्ट ये कंसिडर कर रहे हैं, एंड ith को स्वैप नहीं किए हैं, देन व्हाट्स द
हम्म।
मैक्सिमम। ठीक है।
हाँ जी।
अब मैं i0 को क्या लिख सकता हूँ कि फर्स्ट I माइनस 1 तक। नाउ ये जीरो है, इट मीन्स I पे मेरा फिक्स्ड है कि ai एंड an माइनस 1, ये मैंने स्वैप नहीं किया है, ये फिक्स्ड है। नाउ I माइनस 1 पे दो ऑप्शन हो सकता है, या तो मैं इसको स्वैप किया होऊंगा या स्वैप नहीं किया होऊंगा। ठीक
हाँ
है।
जी।
तो अगर मैंने I माइनस 1 वाले को स्वैप नहीं किया था, तो
हम्म।
मेरा फाइनल dpi0 क्या होगा? अगर इसको स्वैप नहीं किया था, तो यहाँ तक जितने भी
जो
आए
आंसर था वही रहेगा।
प्लस
मतलब अगर
दिस
वो इक्वल रहा होगा
प्लस
तो
दिस।
+1 हो जाएगा।
हाँ, तो ये इक्वल हुआ तो यहाँ प्लस 1 होगा, नहीं इक्वल हुआ तो प्लस 0 होगा।
ओके।
कि ये जस्ट रिप्रेजेंट कर रहा है, ये बुलियन वैल्यू देगा ना, मैं 0 या 1। इक्वल टू।
ओके ओके
तो इक्वल हुआ तो +1 वरना 0, सेम वे फॉर दिस। ओके, एंड सेम
ओके
वे अगर स्वैप किया था तो ये दोनों के इक्वालिटीज चेक होंगे।
ओके।
ठीक है, गॉट इट।
हाँ जी।
Okay, so this was our transition. I hope the state and transition is clear to everyone. Okay, now what would be my base case? If I write the base case, like we can just write for dp
dp
0.
of anything will be 0.
Yeah, so dp of 0, 0, 0, it means if I'm taking a zero based indexing, then for an okay, so in my code, I've taken a zero based indexing. So for dp 0 till here, like in this, we are not comparing with anything. So its output would be 0 only for both the cases. Either we swap it or don't swap it. Here, because we are not checking with anything. So there is no disturbances still here. When we move to 1, then only we would have some disturbance. So they would be computed while calculating the transition. So my base case would be this. dp of 0, 0 and 0, 1, both of them are 0. Okay, I hope the base case, the transition and the state, all the things are clear to you. So we can move to the code now. Okay, so I just took the input. Okay, one more thing. This DP is running till where? This DP is running till n by 2 only. Okay, whatever is the middle element till that, like now there would be two cases for n odd and n even also. So if n is odd, then we would have like we are running, there would be a middle element. Okay, the middlemost element. So we would, if we run the dp till there, then these differences would also get computed. Okay, so we would always run the dp till the middle element. Okay, so the size of my dp would be the seal of n by 2. Okay, so if it is odd, then we do a n plus 1 by 2. And for even also, n plus 1 by 2 would be same as n by 2. So this n plus 1 by 2 would give me the seal of n by 2. This would be the size up till where we are running our dp. Okay, so for odd case, like you can understand, when let's say n is 5, so we would have a0, a1, a2, a3, a4. Okay, so we would run our dp till here a2. So we would have 3 dp states. So size is 3 here. So we would run dp from 0 to 2. Okay, and for even case also, if n was 6. Okay, for even case, okay, so we'll run our dp till here, so that these differences are computed. Now, for even case, if we are running till here, then in this difference would be computed 2 times. So, and if we are running till here, then these differences are computed, but this difference is missed. So this we have to keep in mind, that after computing my dp, what would be this disturbance? If both of a2 and a3, they are equal, either they are swapped or not swapped, they both are only compared. So if they are equal, we do a +1, otherwise we don't do a +1. So this we can do in our final answer. So if n is even, and then we would just compare these two and do a +1 in our final answer if they are equal. So that we can just do separately, so that it's because if we take the dp till here, then this would be considered 2 times. So I'm taking the dp till here only, and this I'm considering as separately. For odd case, there is no problem. If I take the dp till here, both of these are considered. Okay, so I'm taking my dp up till n plus 1 by 2, the seal of n by 2. I've initialized my dp vector as size cross 2. Okay, this is vector of vector int. So size into 2 dp is initialized. Now, as I told you, the base case was dp 0, 0 and 0, 1, they are 0. So I initialized my whole values as 0 only. So base case is covered. So from I equal to 1 up till less than size, I am computing my dp. So first I would compute dp I0 as I wrote in the transition, same thing I have written. dp I0 is I minus 1, 0, this. Okay, dp I0 is dp I minus 1, 0, ai equal to ai minus 1. Okay, so this ai checked with ai minus 1, or a n minus I minus 1 with a n minus I. So a n minus 1 checked with a n minus I. Okay, it would be -1 if you just see for A0, its counterpart is an minus 1. So for AI, its counterpart would be an minus 1 minus 1. Okay, so like in this diagram, if we are taking a zero-based indexing, for AI, its swapping partner would be an minus 1 minus 1. So here it would be an minus I only. So it would be an minus 1 I minus 1, and minus 1 plus 1 would cut each other. Okay. So an minus I, and this is n minus I minus 1. Okay. I hope it's correct now. So that's what I've written in my code. An minus I minus 1 equal to an minus I. Okay, this thing. Okay, so this I've written either this or this. dp I minus 1 1, dp I minus 1 1 plus ai equal to an minus I, ai equal to a n minus I, or plus a n minus I minus 1 equal to a I minus 1, n minus I minus 1 equal to a I minus 1. So this was my dp I0. Same for dp I1. I would just have this thing with like I would just swap this 0 and 1. Rest all remains the same, because if we have swapped the positions of this, if we have swapped this I, we have a n minus I minus 1 here and ai here. So all the comparisons would just interchange. So we can just copy paste this and replace this 0 and 1, interchange this. Okay, I hope both the transitions are clear. We have written these transitions, and then my final answer is minimum of dp size minus 1 0, size minus 1 1. Okay, so when we have computed our dp till, okay, so for odd case, when we have computed our dp till here, which is still a dp of size minus 1, this is covering everything. Okay, so either this would be swapped or not swapped. So taking the minimum among both, swapped or not swapped, this would be my final answer. Only the for the even case, we are just checking this extra. So if n is even, then we would add to the answer a of n by 2 minus 1 equal to a of n by 2. So if n is 6, so n by 2 is 3. So n by 2 minus 1 and n by 2, they both are checked. If they are equal, we would add a plus 1 to our answer. So this way we have computed our final answer and printed it. I hope this is clear to everyone. If we look at the time complexity, we have a dp of size which is order of n into 2. Okay, so this is n by 2, order of n by 2, and this is done 2 times. So overall this is running n times, so order of n, and these are constant operations. So overall time complexity is actually just order of n. And the space complexity, again, this dp is n by 2 into 2, so it is of size n only, and my array is also of size n. So both time and space complexity are of order of n, and with the given constraints of 10 to the power 5, it's easily acceptable. I hope this problem is clear to everyone. If anybody has any doubts in it, you can ask now.
Hello, sir.
Yeah.
Means I don't have got any solution, but for a different question, means it is supposed to be solved faster, no? And many of them is I have also done one solution, means just randomly swiped the both the means n minus one, n minus I and I, that I have swiped both the integers. Then I have means just checked how many disturbances are there. It got accepted.
Okay, like you are telling you have done some greedy approach where exactly what
Yes,
you
means
are
what
doing.
the question said, means I did not thought for a second, miss I just did it, I thought miss it is deep threat, so there will be no miss such complications, so I directly did it,
Yeah,
and
maybe
it
it would have been an easier problem only. I just thought of DP, so I did it like that. Okay, maybe what you are saying that would be acceptable. It's accepted, so obviously that would be the right solution. That would also be the right solution.
is okay.
Okay, like I did it with DP, that's why I explained. But maybe some easier solution exists. So, okay. Okay, like for in this approach, anybody have any other doubt? Like writing this DP was very easy only. Like I just thought that there are two options for any, either we would swap or not swap. So for that, I just wrote the transition and the code is very simple. Okay, like if you are a little comfortable with DP, then you would feel this as simple. Otherwise, obviously, you would not feel very easy with if you have not practiced too much with DP. Okay, I think we can move to the next problem now. Okay, so for the problem D, after a trip with Sakurako, Kasuke was very scared because he forgot about his programming assignment. In this assignment, the teacher gave him an array A of n integers and asked him to calculate the number of non-overlapping segments of the array A such that each segment is considered beautiful. A segment L to R is considered beautiful if the sum from L to R is 0. For a fixed array A, your task is to compute the maximum number of non-overlapping beautiful segments. Okay, so here what you need to do is, for the array A, you just need to compute how many segments are there which sums up to 0. How many maximum non-overlapping segments you can get so that all of those segments sum up to 0. So that's what basically the question is. So if you look at the first test case, here we had, okay, this was an array given to us. Now you just need to find how many maximum non-overlapping segments you can find in this array whose sums up to 0. Okay, so this is one segment, 2 plus 1 minus 3. They would sum up to 0. Okay, and then non-overlapping with it, you cannot find anything else. Another way was there with 2, 1 minus 3, 2, 1. You could have also selected this segment. It also sums up to 0. But if you select this segment and both of them, then this minus 3 is overlapping. So you cannot select both. Either you would select this or you would select this. Okay, so at max, you can select only one non-overlapping segment in this, which sums up to 0. So for this test case, your answer was 1. Okay. Okay, for this test case, your answer was 1. Okay, if we look at the if you look at the second test case, for this, if you see how many non-overlapping segments which sums up to 0, okay, this I can see, this sums up to 0. Any other 4 and minus 4, this sums up to 0. I think here only these two segments are there which sums up to 0. So for this, the answer was 2. Okay, I hope you understood the problem statement, what it is asking you to do. So you need to find maximum non-overlapping segments which sums up to 0. Now again, for this problem, like if you have, okay, what is the like first feeling that you get after looking at this? When would you conclude that there's a segment which sums up to 0? First things that come to your mind is whenever we need to find the sum of a segment, okay, sum of a range from L to R, we can use something like a prefix array. Okay, if you know about the prefix array, that's the first intuition that comes to your mind whenever we need to find the sum of a range from L to R. Okay, now we need to make sure that this sum is 0. So how would be a sum be 0? Now we know through prefix array how we calculate the sum of a range from L to R. That is prefix of R minus prefix of L minus 1. Okay, this is the sum of a range. Now I'm telling that this sum is equal to 0. It means this, if I'm telling that this is equal to 0, it means my prefix R is equal to my prefix L minus 1. So in my prefix array, if we have two elements equal, okay, if we have two elements equal in my prefix array, then I can say if this and this point are equal, then I can say if this is L minus 1 and this is R, so we can say the sum of this whole segment is 0. So whenever if we have computed our prefix array from my initial array, I computed my prefix array. So in my prefix array, if I'm telling that this element and this element is equal, it means if I'm telling that this element and this element is equal, it means this range sums up to 0. That's what I can conclude from this, that whenever I need a sum of 0, I need to have two elements in my prefix array equal. Okay. So that's how segment would be 0. Now, how can we calculate the maximum number of segments which are 0, non-overlapping segments? Okay, so if we go to any element, again, we can like you can get a feel of a DP again here, because whenever you have what you need to do up till here, you would either take till here whatever segments you have, you don't include this in any segment, or include this in one of the segments. So if you take this segment, then maximum number of segments up till here plus 1 would be your answer. And if you don't take this segment, then up till here whatever the number of segments you have, that would be your answer. So I think you got the transition of your DP here, basically, that if you are at an index I, if you are at some index I, either just take the segment ending at this as one of the segment, and from remaining the maximum number of basically segments you get plus 1, or don't include that in any of your segments. So up till here whatever you got. Now the problem here was that how do you compute till where you are getting a sum of 0? If you are going one by one there, then your transition would go order of n. Overall, it would become order of n square. And you can look at the constraints. Order of n square won't be accepted. Okay, just a second. Okay, yeah. I'm audible now. Yeah. So what I was telling is, if you are doing the transition like this, that for I, you are going to every j less than I, and one by one, whenever the sum becomes 0, then you take the DP till there. Then your transition would become order of n. Overall complexity would go n square, which won't be accepted because the constraints for n is given up till 10 to the power 5. So you need to do it in some optimized way. Okay, so what I told here is, okay, I think I moved a little fast. So what I'm trying to explain is, let's tell what DP state I'm taking. So here I'm saying DPI is represents that for sub array A from 0 up till I. Okay, if we have moved till I, so if we are only considering the array up till index I, then what is my answer? That's what my DP state is. So that my DPN would be my final answer. For sub array this, what is the maximum number of non-intersecting, okay, segments, beautiful segments. Beautiful means which sums up to 0. Okay, so this is my DP state that I'm taking. But to write its transition, what I'm telling that if this is the state, what would be its transition is DPI. So either this I would be the end of a segment, or this I would not be involved in any segment. Okay, because we have array till here only. So it cannot be some segment like this because we don't have anything to the right of this for this DP state. Because DPI, we only have array up till I, not ahead of this. So for DPI, if I'm taking a DPI, then either I would have a segment ending at I, or I would not include I any of the segments. So my DPI minus 1 would be one possible answer for this. So it would be either DPI minus 1, where we don't include I in any of the segment, or it would be DP of I minus. Okay, so it would be some DP of J plus 1 such that uh, J plus 1 up till I, this the sum from this is 0. Sum of this range is 0. Okay, or I should write it here. Where J is such an index so that the sum from J plus 1 up till I is 0. J, it is, we need to find such an index so that from J plus I, okay, J is such an index so that from J plus 1 to I, this sum is 0. Okay, so how can we find this J efficiently? That's the main thing. Okay, so this is my DP state, the minimum among either this or this. This is our transition. Now, one way is just go to every J less than I. One by one, just go to every J less than I, and just one by one compute the sum and check if that sum is equal to 0. That would take an order of n transition. Overall, it would become n square. So we need to do this transition in some optimized way. So what we can do is, if we are up till I, uh, what is that J? You can look from here. It is such a J, if prefix sum till I. So if we are at I, then whatever is the prefix sum till I, we need to find any value in my prefix array which is same as prefix I. So we need to find such a J which contains this value of prefix I. Okay, so we can just keep computing our prefix array, and we need to efficiently find where last we found this prefix of I. Okay, where J is the last index where prefix J is equal to prefix I. Okay, this is what my J is. So how can we compute this efficiently is, when we are computing this prefix array, just store the reverse of that in a map. Okay, just store there. Okay, so whenever we computed this prefix of some I, okay, store that in a map denoting its index, so that we can find that what was the last index where we got a value x. Okay, so if my prefix I is x, okay, what I would do, I would store that map of x equal to I, so that when I am at prefix I would need to find, if prefix I is x, what was the last time when I got some value of x in my prefix array. So my MP of x would give me that. And if this MP of x is empty, it means before that we never got a value of x. So for that, this case won't be valid. We cannot make a segment of sum 0 if that is, if before that there is no prefix sum which is equal to x, then we would only use this state. Okay, so this thing we can do by, whenever we are computing it, store it in a map. So in that map, we can search in log n time. So my basically my transitions can be done in order of log n time only. So overall time complexity would be n log n. Okay, I hope it's clear how what we are doing. Would sorting the prefix array help? Like, okay, one more way was that while you are computing the prefix array, store those values in a set which is always sorted. In that you can apply a upper bound lower bound function or a binary search to find your value. Okay, that is also one way. Or if you are stored in a set, that would also, like map is doing that only, the value of a key. Uh, it's like a set only. So you can use a set also for that, or a map also for that. What you told, storing in a sorted way can be done in a set. Okay, so that is also fine. So I hope this is clear to you. We'll move to the code. You'll understand better how I'm implementing it. Okay. So if you look at this, I've taken the input, then I've taken this prefix array. I've computed my prefix array. Okay, it's usual prefix computation. Prefix I is prefix I minus 1 plus AI. Okay. After that, I've declared my DP array. Okay, so what would be my base case? My base case is, okay, I've taken one based indexing here. So my base case is DP of 0. Okay, for one based indexing, this is 1, this is n. DP of 0 is represents an empty array. So for an empty array, what is the number of that? It would be 0. For an empty array, there is no segment. Okay, so DP of 0 equal to 0 is my base case. And we have initialized the map. It would be initialized with MP of 0 as 0. Okay, so we have a value 0. Okay, one more way was in my prefix sum when we get, in my prefix sum when at I, if we are getting a 0 in my prefix array, that prefix I is equal to 0. Okay, that's also the sum of all the elements from this to this is 0. So that can be fine if we are considering that if I'm starting with index 1, then at index 0, if I'm just considering that my prefix 0 is 0, then I can say for any 0, we found a 0. So like my prefix array was initialized with 0. So my prefix 0 is 0. So that's what I'm storing. My map of prefix 0, which was 0, is equal to 0. Okay, so ahead you would understand that this map is updated like this. Map of prefix I is I. It's storing the reverse of my prefix array. The location, the index of my value is what this map is storing. So map of prefix I as I. Okay, so my prefix 0 was 0, so its index is 0, position of 0 is 0. That's the initial case. Now for I equal to 1 to n, we would run a loop. DPI as DPI minus 1, that's one way. DPI is DPI minus 1. Then we would check this if in the map such a j exists, then only we would write this case. Okay, so if in the map we can find this prefix I, if it is not equal to mp dot n, it means we found this prefix I in our map. Then we would say DPI is max of DPI comma. Okay, here not min, we had to maximize this number of segments. It was max. Okay, so max of DPI comma DP of map of prefix I would give me the that j where the last time my prefix I had occurred. So the dpj that I wrote here, this j was such a j, so that sum from j minus 1 to I is 0, which is computed through mp of prefix I. Okay, so dp of j plus 1. So this transition I have written, and I have updated my map of prefix I as I. And my final answer would be dp of n. I hope this is clear to you. What would be my time complexity? This is order of n input. Then prefix computation is order of n. Then my dp initialization, and this loop is running n times. This is this dot find is taking order of log n time, and this is running n times. So this is overall order of n log n. Okay, so we can say that my overall time complexity is order of n log n. Okay, and my overall space complexity would be this array is of size n, this dp is of size n, this map would at max be of size n. So all of n sized uh, data structures we are using, so order of n. So I hope this problem is clear to everyone. Is there any more doubts in this problem to anyone? Okay, so I think we can move to the next problem now. Okay, so Sakurako's exams are over and she did excellent. As a reward, she received a permutation P. Kasuko was not entirely satisfied. Okay, let's ignore this story. A permutation P is considered simple if for every I, one of the following conditions hold. Pi is equal to I or P of I is equal to I. For example, this permutation, these are simple. Okay, so a permutation is simple if at position I we have I, or at position, okay, so this is at position 1 we have 1, at position 2 we have 2, at 3 we have 3, at 4 we have 4. Okay, the other case for it to be simple is at position 1 we have 5 and at position 5 we have 1. Okay, so P of, so if we take I equal to 1, so Pi is 5, so P of 5 is 1. Okay, so P of I was equal to I. So then also it satisfies it. Okay, so basically it just means, if you just look it deeply, that the positions of two of the values are interchanged. So 1 and 5 are interchanged. So then it is satisfied. Here 2 is at its own position. This is satisfied. Now 4 and 3, their positions are interchanged. So this is satisfied. So for this whole array, all of them are satisfying the either this or this condition. So this is also a simple permutation. This is also simple. 1 and 2 are interchanged. Now for this, if you look at position 1, there is a 2. At position 2, there is a 3. At position 3, there is a 1. So it is not an interchange or a pi equal to I. Uh, it is completely different. So this is not a simple permutation. Same way for this. Now, in one operation, Kasuke can choose index I and j and pj. Sakurako is about to return home. Your task is to calculate the minimum number of operations that Kasuke needs to perform to make the permutation simple. Okay, so the operations given here is just pick two indices and swap pi and pj. Okay, now you need to find the minimum number of swaps that you need to do in order to make the permutation simple. Okay, if it is already simple, your answer would be 0. But if it is not simple, you need to do some swaps. So you need to find the minimum number of swaps you need to do so to make it simple. Okay, so if you look for, this was already simple, so answer is 0. This was already simple, so answer is 0. Now, if you look at this was not simple for already. So for this, what we can do is, so here if you see, indexing is 1, 2, 3, 4, 5. So at index 1, we have 2. At index 2, we have 3. At index 3, we have 4. At 4, we have 5. At 5, we have 1. Okay, so this is not simple. You need to do some swaps to make it simple. So what swaps you can do here is, okay, one possible way is, let's say you swap 2 and 3. You got a 3 here, a 2 here. And then let's say you swap, okay, you got 2, 3, 4, 5, 1 after making that swap. And let's say you can swap 4 with 5, I guess. 4 with 1. Yes, 4 with 1. If you swap 4 with 1, you get 3, 2, 1, 5, 4. Okay. So after making these two swaps, this swap and this swap, in this permutation, if you look, 1 and 3, they are interchanged. 2 is at 2, 4 and 5, they are interchanged. So this is completely fine. This is a simple permutation. So in two swaps, you were able to make it simple. So answer for this test case would be 2. You can look, answer for this test case was 2. Okay. So this is what you need to do. You need to find minimum number of, like in more number of swaps, you could have done this, but the minimum was 2. So your answer is 2 here. So you need to find the minimum number of swaps to make it basically simple. So how can you do this? If you look at the constraints, my n is up till 10 to the power 6. So you need to do something in order of n only, or at max n log n. Okay, not more than that. So how can you do that? Okay, so let's look at some observations to see what we can do. Okay, when is a permutation simple? So if we like try to like draw this, what we are doing is P of I is equal to I was one case and Pi equal to I was another case. Okay. It may happen that we get P of I is equal to I, or we may get P of I equal to I. Like these cases can also happen. What basically these represents again and again doing P. If you just look closely, if I'm taking I equal to 1 here, when do I get 1 back if we repeatedly do this P? Okay. P of 1 was 2. Okay. So I am telling that P of 1 was 2. Okay. Then with 2, I did again P of 2. P of 2 is 3. I got a 3. Then with 3 again, I did a P of 3. P of 3 was 4. I got a 4. With 4 again, I did a P of 4. P of 4 was 5. I got 5. With 5 again, I did a P of 5 and P of 5 was 1. So I got back to, okay, after doing a, with 5, after doing a P of 5, I got back to 1. Okay, so if you look, what is happening here is a cycle is forming from 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 1. Okay, if you look, if we start with 1, then P of 1 is taking me to 2. Okay, P of 1 is taking me to 2. Then P of 2 is taking me to 3. P of 3 is taking me to 4. P of 4 is taking me to 5. P of 5 is taking me to 1. So this is forming a cycle. Now, if you start with I equal to 2, what would happen? I equal to 2. P of 2 would take me to 3. P of 2 would take me to 3. Then again, P of 3 would take me to 4. P of 3 would take me to 4. This way the cycle would continue and we would get back to 2 after this. So if you start with any value among these, they would move in a cycle and come back. Okay. So we have this cycle of length 5. Okay. Now, when are we okay with a cycle? Is when we have P of I equal to I. What does that mean? That if I is something, let's say we have a 1, then P of 1 is 2. Okay. And P of 1 is 1. That's what this condition is saying. That means if we have a cycle of length 2, two elements with each other, that is fine. Or if we have a self cycle, P of I equal to I, it means with 1, we are going back to 1. Okay. So these two things are fine. Either we have a self cycle or we have a cycle of length 2, then we are absolutely fine. Now, whenever we have a cycle of length greater than 2, whenever we have something from 1, we are going to 2, we are going to 3 and then back to 1. Okay, this is a cycle of length 3. This is a cycle of length 5. We may have a cycle of length 4. Okay. So basically, if we look at this permutation, we can just divide this permutation into different cycles of different lengths. So we would need to make every cycle to be less than equal to 2 length. That's what we need to do. Okay, so how can we break this cycle? Okay, if you have a cycle of length 3, how can we break this? Oh, an example of this would be if we have 231. 231 is your permutation. Okay, if you have a permutation 231, then if you are starting with I equal to 1, then P1 is 2, you move to 2. P2 is 3, you move to 3. P3 is 1, you move to 1. This is the cycle you get. Okay. So for this permutation, how can you make it simple? That you have cycles of length less than equal to 2 only. So if you just do any swap in this, let's say we swap these 3 and 2, then P2 is 2 and these two are swapped with each other. This is simple. Okay. So what happened when we swap these two? If you look at this graph, 1 was pointing to 2, now 1 is pointing to 3. So this 1 which was pointing to 2, now it is pointing to 3. So this edge got removed. It's now here. And for this 2 which was pointing to 3, This 2 which was pointing to 3, now it is pointing to 2 only. So instead of pointing to 3, now it is pointing to itself. Okay, so that is what happened here. So this way we got a cycle of length 2 and a self cycle. So this way we were able to make it simple. So whenever we have a cycle of length 3, just swap any two elements, it would become simple. Okay, what about a cycle of length 4? Okay, so just analyze these cycles to get in how many minimum number of operations you can basically reduce it into a simple permutation. So if you have a cycle of length 4, can you make it in minimum number of ways? Is you have this arrow, make this arrow go there, and you have this arrow pointing there, make it go there. Basically just swap the values of this 4 and 2. If you swap their values, so this 2 was containing 3, now this 2 would be containing. Okay, so we would swap 1 is pointing to 2, it would point to 4 now. This 3 which was pointing to 4, it would point to 2 now. Okay, we would swap 1 and 3. Okay, let's say we swap 1 and 3. So this 1 was pointing to 2. Now it would point to where 3 was pointing, which is 4. And this 3 was pointing to 4, it would point to where 1 was pointing, which is 2. Okay, so in one swap, we can make it a pair of this. Okay, like from the permutation, if you want to understand, it's this. Okay, for this permutation, this was the like graph given to us. For this permutation, we have from 1, we go to 2, from 2, we go to 3, 3 to 4, 4 to 1. Okay, this was the graph. Now, when we swap this, okay, just swap two elements of 1 and 3. Okay, so at position 1 and 3, this 2 and 4 got swapped to 4 and 2. Okay, so now 1 which was pointing to 2, it is now pointing to 4. Okay, and this 3 which was pointing to 4 is now pointing to 2. Okay, so this way we were able to make reduce the cycle into sizes of 2 in just one swap. So for any cycle of size 4, we can say we can reduce it in one swap. So we know a cycle of size 3 can be reduced in one swap. Cycle of size 4 can be reduced in one swap. What about a cycle of size 5? So if you look at this cycle of size 5, now if you just try to reduce in one swap, you won't be able to do it in one swap. Like you can just like from the 4, you can understand if you had a cycle of size 4, you can just swap two of the arrows, make them point there and make it in one swap. But if you have 4 elements, like if you just swap any two of the arrows, you won't be able to make it completely. Okay, so like if you swap this and this, let's say, okay, so this was pointing to 4, this was pointing to 1. So now this would point to 1 instead of 4, and this would point to 4 instead of 1. Okay, so if we do it like this is okay. Now this again we got a cycle of size 3, which would require one more swap in order to break it. Okay, so for a size 5, we know we would require at least 2 swaps. Okay, from just looking, you can analyze and understand that for 5, minimum of 2 swaps would be required. In one swap, you can never break it down into components of just 2. Okay, so from that we can understand, like whenever we have something of size 6, okay, so like with one swap, you can just break it down into components of 3 and 3. Okay, so these two arrows would, this arrow would get removed and they would move here. It would be break down into size of 3 and 3. And like here also in 2 swap, you could do it. Okay, so for size 6 also, you could do it in 2 swaps. Okay, I'll show you. Okay, we have something like this. Okay, what you can do is, let's say you swap this and this. So this thing would get removed. This thing would get removed and it would point here, and whatever was pointing there, this thing would get removed and it would point there. Okay, so in one swap you made it like this, and then you have a component of size 4 which can be done in one more swap. Okay, so likewise for 6 also you can do it in two swaps. Now when you would move to 7 you would require three swaps. Okay, so basically for every 2 you would require three swaps, for 9 you would require four swaps. Okay, so just by looking and some small analysis you can find this pattern. So basically you can say that whatever number of elements, for 3 elements you require 1, for 4 you require 1. So you can just group them up. So basically if you do n by 2, okay, so this n by 2 of this would return, or the seal of n by 2 of this would be 2, seal of n by 2 of this would be 3, its seal would be 4. Okay, so for 2 you have 1, for 3 you have 2, so seal of n by 2 minus 1. Okay, so this is the final formula. You can say if the length of your cycle is n, okay, then seal of n by 2 plus 1 would be the number of operations required, number of swaps required to reduce it into a simple permutation. Okay, so this can be written as n plus 1 by 2 minus 1, which is same as n minus 1 by 2. So in my code, I have written n minus 1 by 2. So don't get confused when you would look at the code. You can write it in any way. Okay, so this is the formula that we derived. So what we would do is we would divide this permutation, whatever input permutation we are given, we would divide it into cycles. We would find the length of those cycles. And for every cycle, whatever is its length, according to the length, we would add this much to our answer. So that would be my final answer. Now, how can we divide this permutation and find the length of the cycles? Is if you are given some permutation, let's say you are given 2, 3, 1, or let's say 2, 3, 1, 5, 6, 4. Okay, if you are given this permutation, what you can do is from 1, whatever would come in the cycle of 1 is by moving with p of 1, p of whatever we get. If you just one by one move, start with I equal to 1, then go to 2. Okay, go to p of I. If you update p as I as p of I, you would go to 2. Then if you update again I as p of I, you would go to 3. Then you would go back to 1. So until we reach 1 back, till that we would traverse. Okay, so we would just keep updating I as p of I, while, okay, if we are starting with, okay, let's say if you are starting with j, then we would keep updating our j as p of j. Okay, so while j doesn't become equal to I again, till that if we traverse like this, so this way we can compute the length of the cycle. Here we can do a count plus plus. So I hope you understand. So we would just keep updating j as p of j until j becomes equal to I once again. Okay. So we'll initialize j as p of I. Otherwise, initially only they would become equal. So start with I equal to 1, initialize it as p of I, which is j as 0. Just keep updating it like this. The number of times this loop is running, that would be the length of the cycle. So we would get a cycle of length 3 here. After that, to whichever element you already traverse, just mark them up so that you don't count them again. Then you start counting from 4 which was not visited. Okay, so just make a visited array or a check. Whichever j you already traversed in this while loop, don't traverse it again. Okay, so this group would have a 3 length, this group would have a 3 length. Okay, so that way just we can traverse this whole permutation and group it into cycles of different lengths. For every cycle of any length, n by 2 seal plus 1, add that to your answer, where n is the length of the cycle. Okay, I hope you got. Yeah, sure, you can unmute and ask if you want to ask a question.
Sir, I basically we are doing like finding the cycles and the we want to find the size of the cycle. Yes.
Yeah, yeah. For
May
this
I share
purpose,
my yes, yes.
yeah.
May could I share my code like I also trying to do this thing by using some maps and sets like that, but
Okay,
I am
you can share.
I got TLE,
I'll look
so
at it at okay, I'll look at it at the end of the PCD. You can share in the chat.
can
Okay,
I
I'll
share now or
explain.
could I share now or like in
Yeah, you can share now. I'll look at the end. Okay.
okay. Thank you, thank you.
Okay, so let's look at the code. So what I explained you here is we'll go to every element, find the length of the cycle using this, and then add and seal of n by 2 plus 1 to our answer. So that's what I'm doing here. I've taken the input. This is the input part. Then I've just maintained this check, or you can say it as visited uh, the indexes which are already visited. Okay, so initially none of them are visited, so marked it with 0. Now I would start with I equal to 1, go up till n. This is a loop from I equal to 1 up till n. If check I is already 1, we have already visited it before only, then do a continue. Otherwise, j equal to pi, as I told you. This is the code to find the length of the cycle. J is equal to pi. Initialize a counter with, okay, you can initialize it with 0. Why I've done it with 1, I'll tell. While j is not equal to I, j equal to pi and count plus plus. And also mark j as visited. So check of j as 1. This way I'm computing the length of the cycle. Now, if I initialize it with 0, so if you look for this cycle of length 3, if I start with I equal to 1, then my j would be p of I, which would be 2. Then I'll enter this loop, then j would be updated to 3. Then again, I'll enter this loop, j would be updated to 1. I'll break out of the loop. So I entered the loop only 2 times. My count was only done plus plus 2 times. So basically, the number of times this loop is running plus 1 is the length of my cycle. Okay, so that's why I'm initialize count as 1 and then doing plus 1. Okay, number of times this loop is running plus 1 is the length of my cycle. So check I also I have marked as visited. And then if count is less than equal to 2, then just do a continue. If cycle is length of cycle is less than 2, no problem. Otherwise, count minus 1 by 2. Okay, as I told that the thing that I had written there, this seal of n by 2 minus 1 is same as n plus 1 by 2 minus 1, or which is same as n minus 1 by 2. Okay, so n is count here, so count minus 1 by 2 is what I have added to my answer, and I've printed my final answer. I hope this code is clear to you. If there is any doubt in this implementation, you can ask. Okay, if you look at the time complexity, this is the input part order of n. Here this loop is running n times. This is simple if condition. Now this while loop is running inside this for loop, but every time it is running, I'm marking a j as 1. So at max, and if I've already run that here I would mark it as continue. So at max, I'm running n times only, either here or here. Okay. So at max, I'm running overall n times only. Every element is like processed once only. So this overall is running n times only. I hope you understand. We have a while loop, but inside a while loop, we are doing check of j as 1. So this is an overall n times. Okay, so I hope you understand the overall time complexity would be order of n here. And my space complexity would also be order of n. We have a check of size n and a p of size n, nothing else. Okay, so I hope this problem is clear to everyone. So we can move to the next problem now. Okay, so problem F. So Kasuke is too lazy, so he'll directly give you the task. Fibonacci number, that's the definition. I hope you know what a Fibonacci number is. This is what it is. F of 1 and 2, they are 1, and then rest of them are computed as sum of the previous two elements. We denote G and K as an index of the nth Fibonacci number that is divisible by K. For given n and K, compute G of n comma K. As this number can be too big, output it modulo 1 plus 7. So you just need to find the nth Fibonacci number that is divisible by K. So for example, G32, it means the third Fibonacci number divisible by 2. So here if you see the Fibonacci sequence, the first Fibonacci number divisible by 2 is here. This is the second and this is the third. So the index, you need to return the index of the nth Fibonacci number divisible by K. So index of this 34 is 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 was the index of this 34, which was the third element divisible by 2. Okay, so my answer of G32 was 9. So you are just given n and k. For every test case, you need to find G of n k. N is up till 10 to the power 18 here, but k is only up till 10 to the power 5 here. And guarantees the sum of k across all test cases is 10 to the power 6. So let's find out. Okay, so this question I would say was a pure observation based. Okay, so like I hope you understood the question, what is telling. G of 32 is 9, how it's getting computed. Now for any k, we just need to find, if let's say k is 2, then what's the first, like we need to find nth number divisible by 2. First number divisible by 2 was at third index, then at sixth index, then at ninth index. Okay, third, sixth, ninth. For 2, I can like prove it also. If you just look at Fibonacci numbers, it is 1, 1, 2, 3, 5, 8, 13. Likewise, okay, this is index 1, 2, 3, 4, 5, 6, 7. If you look at the parity of the numbers, the first number is an odd, second number is odd. Now the third number is sum of these two numbers. Now sum of any two odd numbers would always be even. Now if you look at the fourth number, thus this is sum of an odd number and an even number. Sum of odd plus even would always be odd. If you look at the fifth number, it is sum of even plus odd, it would be odd. Then sum of odd plus odd, it would be even. So this sequence is repeating: odd plus odd, odd, even plus odd, odd plus odd, even. So always you had odd, odd, even, odd, odd, even, odd, odd, even. So an even number would always occur at multiples of 3. Okay. So for k equal to 2, you can like, I have proved it only that for k equal to 2, your answer would be just n into 3. That would be your answer. Like for n equal to 1, your answer would be 3. N equal to 2, second position is 6, third position is 9. So n into 3 is your answer for k equal to 2. Now what about other values? If you just try to do the same type of observation, okay, like I'll give you a bigger Fibonacci series here. Okay, just look at this Fibonacci series. For k equal to 2, you understood. For k equal to 1, obviously all the numbers are divisible by 1. Just do multiplied by n. That would be your answer. Now for uh, k equal to 3, what all numbers are divisible by 3? The first number divisible by 3 is this 3, which is the fourth number. Okay, then the number divisible by 3, this is not, this is divisible by 3, the eighth number. Okay, then the next number divisible by 3. Okay, if you look, okay, the first number divisible by 3 was this. Next number divisible by 3 was this. Then this is not mm, this number. This is divisible by 3. Okay, this is not. This number is again divisible by 3. So if you look for k equal to 3, you can say 4th, 8th, 12th, 16th. So with multiples of 4, I am getting. So for k equal to 3, I can say my answer is 4n. Multiples of 4. Now let's analyze for other k. Let's say for k equal to 4, what would be my answer? So what all numbers are divisible by 4? Not divisible, not. This number is divisible by 4. The sixth number. This is not. This number is divisible by 4. This is not. Again, you would get the 18th number, which would be divisible by 4. So again, you can see multiples of 6. Sixth number, 12th number, 18th number. They are divisible by 4. So for k equal to 4, you get 6n as your answer. So you can see, like, this was just pure observation. I don't have a proof why this is happening. Maybe you may read the editorial there, some proof would have been given, but I also don't have a proof. But just by looking at the observation, I concluded that for any k, this pattern would only exist, that for any k, we would have some multiples of some x where we would get values which are divisible by k. So what I concluded is that for k equal to 2, my answer was in multiples of 3. For k equal to 3, my answer was in multiples of 4. For k equal to 4, my answer was in multiples of 6. If you look at k equal to 5, my answer was in multiples of. This was the first number which is divisible by 5. Then this is divisible by 5. This is divisible by 5. So multiples of 5. Likewise, for every number, you would have that number in. For every k, you would have n into some multiples. Okay. So what is this value? These values are the first index where the Fibonacci number is divisible by k. So the first index where the Fibonacci number is divisible by 2 is 3. 4 is the first index where the Fibonacci of 4, I would say, Fibonacci of 4 is divisible by 3. This is the first index where it is divisible by 3. 6 is the first index where it is divisible by 4. 5 is the first index where it is divisible by 5. So for any k, if you can find the, for any k, if you can find the first index I such that Fibonacci of I is divisible by k. Okay. So if you can compute the first index I such that Fibonacci of this is divisible by k, I'm telling this as, let's say, dp of k or whatever you want to call, like function of k, and not telling it as dp. Function of k is this, then my final answer would just be n times function of k, n modulo m, obviously. Okay. So how can you compute the first index I such that Fibonacci of I is divisible by k? Now, here the problem was, if you look at the problem, the k was up till 10 to the power 5. Okay, so for some numbers, you were getting these values initially only. Now, if we want to find for, let's say, 11, okay, we got it somewhere at F12. Okay, if we want to find for some 10, we got it here, F15. So if you go to move to higher values, they would go to some really large really large indexes, which whose values cannot be stored in even long. Okay, it would go par 10 to the power 10 because this Fibonacci series is rising exponentially. So if you are computing this, just if you're computing all the values and then checking whether they are divisible by k or not, okay, after 10 to the power 18, you cannot store the greater values. So what you can do, you just need to compute whether they are divisible by k or not. Okay, what is the first number that is divisible by k? So compute the Fibonacci series modulo k. Compute the Fibonacci series modulo k. Whenever you get a 0 in your Fibonacci series, that's the first index where uh, that's the first index where this Fibonacci series is divisible by k. Okay, so compute the Fibonacci series modulo k, and the first value where you get a 0, that would be the function of k. You can write your final answer like this. Now, what would be this range of the first value where that would be divisible by k? What would be the, like, if you just do a brute force, would it be accepted? So what I did is I just tried whether it would get accepted. Now, so I just ran a loop from for every I from basically 2 to till where I can reach. Okay, just start computing the Fibonacci series modulo k. Whenever I get an element of the Fibonacci series which is 0, I just break out of the loop and tell that that index, wherever that ith index is my f of k. Okay, that ith index is my f of k. Just do n into that modulo m. Now, what time complexity it would take to compute that? So at max, if k is going up till 10 to the power 5, so for any k up till 10 to the power 5, what would be the first index where this Fibonacci series modulo k would become 0? That is going something in order of k only, because I just wrote the code and it got accepted. I don't know the exact time complexity of what, like, you'll have to see some mathematical proof of why it is something of the order k, but it is something of the order k only, like 2k, 3k, 4k, that only, because uh it's not too large. Like you can see, for 2 it was 3, for 3 it was 4, for 4 it was 6, for 5 it was 5. So it is something near about k only, like 2k, 3k. Okay, so for higher values also it is not going very large. Okay, for k up till 10 to the power 5, it's not going more than 10 to the power 7, that I can say, because my code got accepted and that got accepted in very less time only. Okay, so I don't know the exact what its time complexity would be, because that would come from some mathematics, but this is something less only which can get accepted for k less than 10 to the power 5. Okay, so I hope you understood the logic. I'll just do a brute force, just compute my Fibonacci series modulo k. Whenever I get a 0, I'll stop there, find that index, that's my f of k, and n into f of k modulo m is my final answer. Okay, so let's look at the code. So here, for k equal to 1, that base case you can cover is when k is 1, all the numbers are divisible by 1. So the nth index is your answer. So n modulo m. N can go up till 10 to the power 18. So do a mod m, because you need to find your final answer as modulo m. So just see out whatever it returned. Otherwise, I computed my Fibonacci series. The first element is 1, second element is 1, and this j index is 2. So I'm at it. This is the I'm at second element, so j is 2. Now I'm running an while one loop, an infinite loop. C is a plus b modulo k. This is my current element of my Fibonacci series. I do a j plus plus. Okay, the current element is the sum of previous two elements. If this c is becomes 0, okay, I'm already doing a mod k. I'm computing it in terms of mod k only. So if this c becomes 0, then c out n into j mod m. Okay, n mod m into j mod m. C out that and just return. Okay, otherwise, just go to the next Fibonacci number, update A as B, B as C. Okay, so you just move your series. So A was my first element, B was my second. So my first element is now the second element. Second element is now the third element. The new third element would be computed after that. Okay, so this way I'm computing my Fibonacci series. Whenever I get a 0, J is the index of my Fibonacci series. So N into J is my answer. That way, this code got accepted. So time complexity, I would say, is, I don't know exact, but it's something in the order of k only, I suppose. Okay, so that's what I would say. And for space complexity, I would say this some simple variables, so it's order of 1 only. Okay, for each test case. I hope this code is clear to you. It was purely an observation based question. Okay, you had to just observe these things. Okay, in the tutorial, maybe you can find the mathematical proofs to that. Maybe I'll attach the proof in the comment also if it's there. Okay, but I did it just by observation. Okay, just by looking at the Fibonacci series. Okay, so I hope it is clear to you. If there's any more doubts, you can ask. Okay, we can stop the recording now. Thank you very
Where can we
much.
find this recording?